Everyone, I'm glad to be here and share our work on formalizing a complete semantics of eBPF instruction set architecture for Solana. First, I would like to introduce the background. Solana is a third-generation high-performance blockchain platform. It provides a fast execution environment based on an eBPF-powered virtual machine written in Rust. However, as highlighted by security audits, the Solana eBPF VM is still not formally verified, leading to risks such as infinite loops and branch handling bugs. This motivates our work to formalize the semantics of the Solana ISA, and thus we can prove the correctness of its virtual machine. And this is the workflow of the Solana eBPF VM. Smart contracts are first compiled into bytecode and then checked by the verifier, and finally will be executed either by the interpreter or by the x64 just-in-time compiler. So our work at OOPSLA'25 focusing on providing the eBPF semantics, while our earlier work at Stella 2024 provides the necessary x64 semantics for the just-in-time compiler. Our goal is simple yet fundamental: to build a rigorous machine-checked foundation for understanding, verifying, and securing the Solana eBPF VM. And for the related work, let's first look at Linux eBPF. eBPF stands for Standard Berkeley Packet Filter. It basically lets you run sandboxed programs inside the Linux kernel, so you can add new features or monitor things without actually changing the kernel itself. When it comes to Linux eBPF, there is already a lot of research out there focusing on the verifier, interpreter, and the just-in-time compilers. But for Solana, this research is still quite limited. Most existing work depends on testing or fuzzing, and so far there hasn't been any formal verification for the Solana eBPF. Now let me talk about the challenges we faced. First, at the instruction level, Solana eBPF is a bit different from the Linux eBPF. It adds 13 new instructions, and some of the existing semantics are also changed. Second, at the Rust implementation level, things get tricky because Rust semantics are quite complex, and sometimes they don't fully match the definitions in Isabelle. For example, operation flag integer division and modulo behave slightly different. Finally, at the verification level, we don't yet have a trusted compiler to make sure that our formal model faithfully reflects the original Rust implementation. Now, to address these challenges, we've made the following contribution. First, we provide a complete formal semantics of the Solana eBPF instruction set architecture. All 116 Solana OP codes formalized and their semantics mechanized in Isabelle. And second, we built a semantic validation framework to check the consistency between the Isabelle formalized semantics and the Rust implementation. Third, we demonstrate some applications of our formalization. And based on the semantics we developed, we further model and verify several Solana components. For example, we check the consistency between the assembler and the disassembler, and so on. Now I'll move on to the formalization of the Solana eBPF, or SBPF for short. First, for the syntax, we defined several basic components: registers, memory block, and instruction forms. It's worth noting that the common ISH is shared between all versions, while some instructions are version-specific, like the signed and unsigned multiple high and low double word are specific to version 2. And we also describe the program state. Each state contains 5 parts: the register state, the memory model, the stack, the version, and the call map. And now we move on to the semantics. Our approach is directly based on the source code. For example, here's the negate 32 instruction in Rust code, and we turn this behavior into a semantic rule, which describes when the instruction can be executed and how it changed the program state. Finally, we mechanize these rules in Isabelle so that our semantics can be checked by the proof assistant. And we use small step operational semantics here. For example, here are some arithmetic logic unit unit instructions. And I won't go into details here. You can find more in the paper, or we can discuss later. Now we come to the third part, validation. The key question here is how do we make sure that our formal semantics is consistent with the original Rust implementation? For example, in some cases, a single instruction can actually be interpreted in more than one way. We need to find out the exact correct version. And in other cases, even if you get the correct translation, you will find that some simple operators like modulo behave differently in Rust compared to Isabelle definitions. So that's why validation is crucial. It helps us bridge the gap between the two systems, the semantic gap. And to solve this problem, we made the semantics executable by generating OCaml code directly through the Isabelle's built-in code extraction facility. We first conduct the program-level validation by running the Solana official test suite. It includes 114 normal cases and 32 exception cases. We have to exclude 14 cases because they require modeling Solana's built-in system calls. And furthermore, we also perform the instruction-level validation, which means that we execute one instruction at a time, both on OCaml and Rust, and compare the resulting register state and memory model. We tested all the instructions except call and exit, since they require a full Solana program structure. And in theory, this framework can support any number of tests. And each round can run over 100,000 cases. And we've completed several rounds so far. And all the results matched perfectly, which shows that our semantics is valid. When we are using the extracted code, we actually found it quite hard to work with. For example, simple natural numbers ended up in deeply nested constructors that are difficult for humans to comprehend. This makes the extracted code difficult to integrate with our systems. So we introduced glue code. Basically, it's an interface layer that connects Isabelle with standard OCaml code. It wraps the Isabelle's complex types and converts them into integers. We use the wrapped Isabelle model to extract OCaml code. Until now, it's still hard for direct use. So we add another glue code by translating OCaml ints into Isabelle ints, and so that we can feed the test cases in normal way. Therefore, the extracted OCaml code can be much easier for you to use for our validation. And in the fourth part, we show how formal semantics can be applied. First, we apply to the assembler and disassembler to prove the correctness of the translation between the assemblies and the binaries. Second, we applied it to the verifier to make sure that the interpreter executes without errors in one step. And third, we use it for the x86-64 just-in-time compiler, where we validate the compiler correctness for Solana's basic arithmetic instruction to x64 binaries. And for evaluation, the overall effort is 11 person-months in total. Most of the effort, around 60%, went into eBPF verification, and about 30% went into the x64 binary formalization. And the remaining 10 was used for building the verification framework. We also report issues back to the Solana community. First, we found that the interpreter and the just-in-time compiler lack proper version checks, which means instructions specific to version 2 could mistakenly run in all versions. And second, the assembler does not check the source register range, which break the consistency between the assembler and the disassembler. And to conclude, this is the first complete semantic study for Solana, fully mechanized in Isabelle Hall. We also built an extensible validation framework to ensure the semantics, the formalized semantics and the real-world implementation are consistent. Finally, our work opens the door for broader applications, including formalization of several Solana components and the verification of properties. And thank you so much. This is the QR code for our GitHub repository. Anyway.
So we have time for a couple of questions. Any questions? Yeah, you can use the microphone.
Thank you for the talk. It's kind of a minor question. Why are there differences in the module function between Rust and Isabelle? Like, it feels like a very simple.
It's hard to. You can see this form. We have listed the different results in the modulo operator behavior. As you can see, the same equation, in Rust will end up in -1, but in Isabelle it will be 9. So this is a kind of sometimes the modulo end up with the positive number, and sometimes it always ends up with a -1.
Oh, okay.
Yeah.
Thank you.
My question is, so you have this kind of way to essentially verify, give the semantics to a Rust program in a sense. Did you struggle with some of the Rust specific features, so like say borrowing or mutable references and so on?
Actually, because it's Rust to Isabelle, so Isabelle doesn't have the ownership system or borrow checkers, so we don't struggling with the ownership system actually. If it was the other way around, then we would have to consider this problem.
Mm-hmm. Okay, thank you.
Thank you.
More questions? Okay, so let's thank the speaker.